while doing the correlation analysis, we can also ask it to compute the residuals. So let's say predicted value, unstandardized residuals. We are asking it to compute the residuals. What these Cook's distance is? Cook's distance is the distance of the outliers from the mean. So if the Cook's distance is high, this is one of the techniques how to find out the outliers or see which points which data points are outliers in your data set. So we have asked SPSS to compute the residuals for us. Okay, and let's go here and see. You see these residuals that SPSS computed. Now this is the difference. Minus 2.62 is the difference between the value value of y that we estimated using our model and the observed y. So this is residuals. So that is how we use our SPSS tool to develop a regression model. Now let's do this regression model again and take out the values which are not let's just keep posted speed limit and segment length, and then develop the model again, and let's see what happens. What do we see here? So let's see. The value of R square is, the value of R square is reduced from 0.79 or 7 something to 0.67, which means in our the regression model, the more independent variables we have, the stronger the model is. However, it's not necessary that the model that we have is reliable as well. So since we deleted some of the variables from our model, our R square value reduced, but it's still better. It's something which is like in the practical world, it's very difficult to have a value of 0.9 or 0.8 or 1. So we'll still keep this model, and let's see how is it behaving here. So the signs are good. As we increase the posted speed, the speed limit increase. The speed of the vehicle increases. As we increase the length of the roadways without signals, the speed increases. The signs are good. The significant values, see both of them are 0, which is less than 0.05. It's saying that both of these variables, they have a good relationship, or they explain our dependent variables well. Variance inflation factor, again, it's less than 4, so our assumption is that there is no multicollinearity in our model is satisfied. Let's see here. See, this one is better. It's more closer to the to this straight line, which means our second assumption is met better here as compared to the first one, that all the errors are normally distributed. We see randomness here, though there are still some points which are we are seeing some pattern here, but again, that's better than the first one. And this is, since we had a low value of R, you see that the scatter between this observed speed and this standardized predicted value has increased a little bit, since the strength of our model has reduced. And let's see what our residual values are. Are they more? Are they less? See, the residual increased because now we have just two variables explaining. So it's kind of a trade-off. You not necessarily include all the variables, independent variables, just to make your model stronger, because some of the variables are not contributing at all. So it's kind of a trial and error, and then you come up with a model which is not only strong, but it's reliable as well. And it meets all your assumptions that for regression analysis. So clear so far? Everyone? Okay, let me bring in what is the question? Okay, let me.
Hello? Yes, the smart data, just use it for now, because it's only familiar to smart. The student
Yes?
the data with you. Hello? I'm just asking that leave it. Because it's only familiar to him, and we have to go with the whole class, not the individual student. And the area is staff one, but please actually use this one. Okay? Yeah, he can consult you through email.
Okay. So small, what we can do is you can send me your question. You have my email address. You can always send me a question. Okay. Again, then we'll go on from there. So, do on any of any other question that we can discuss today? Something which related to any other lectures, like our previous lectures or today's lecture, something which is not clear to you? Any question in mind? Anyone? Or all of you are fine? Okay. So multicollinearity is a way to find out whether our independent variables are related with each other or not. Ideally, our independent variables should not be related with each other, because when we change one independent variable and we want to see how much it affects the dependent variable, since the two independent variables are related, the other will change as well. We do not want that in our regression model. One of the assumptions, or not the assumption, but one of the tests of a regression model is that there should not be a multicollinearity or a collinearity between the independent variables. To test that, we call that situation multicollinearity. If two or more than two independent variables are related with each other, that kind of creates a circulation, and that is what we call multicollinearity. We do a test for that. We do a multicollinearity diagnostic or collinearity diagnostic. And how do we know whether the independent variables are related with each other or not? So let's take example of two variables. Let's say that the amount of biomass in wastewater and the amount of let's say some bacteria. So are the bacteria and biomass are highly correlated with each other or not? Both of these are independent variables, and we want to see whether they are correlated with each other or not, or do they create a multicollinearity in our regression model. What the SPSS does, or what the methodology is, that it develops a regression model between two independent variables. So it takes one independent variable as a dependent variable and other independent variable it keeps as an independent. It conducts a regression analysis, and then it comes up with the value of R square. Now it uses that R square to find out the tolerance, which is 1 minus R square, and the other thing is the variance inflation factor, which is 1 divided by the tolerance. So for two variables, independent variables, not to be linearly related with each other, or for a model not have a multicollinearity into it, the value of VIF, or variance inflation factor, for each independent variable should be less than 4. Is it clear now what the multicollinearity, as the name explains, collinearity, which means the independent variables are linearly related with each other, and multi means more than one variable. So clear now? Yes? Okay. Any other question? All of you are good? Okay, if they are high score, then take out it's a tough to see which variable is like more significant, so you can take out one or the other. Okay, so that concludes our statistics lecture session. And if you have any questions related to my previous lectures or to this lecture, send me an email, and the file that I got today, the file card, we'll discuss that. I'll look at it, and then send me your questions. Send me the questions that you want me to look at, and then we can discuss that later, okay, via email. So feel free to send me an email if you have any question related to this lecture or to the previous lecture. So I wish you good luck, and hope all of you will do well in your studies. Thank you.